Hello friends. So after having understood what are crystalline and amorphous solids, we have also seen the various types of crystalline solids. Today we shall understand how the constituent particles in a crystalline solid are arranged, giving rise to that crystalline structure. So for that we need to understand the term unit cell. Now what do you mean by this term unit cell? If you look at the microscopic view of the crystalline solid, you will see that there are many such patterns which are repeating time and again in various directions. So if I were to pick out one such pattern that is repeating in all the directions, then this one pattern would be called as the unit cell. It is very much similar to making a rangoli out of dots. So after placing the dots, you construct a pattern out using a set of dots, and then you just go on replicating the same pattern in all directions in order to get a bigger rangoli design. So much the same in a crystalline solid, you have many dots. These dots are called as lattice points, and these are the points at which the constituent particles of the crystalline solid are present. These particles may be molecules, atoms, or ions. Whatever they may be, the position at which these points are present are called as the lattice points. Now, if you draw some imaginary lines connecting these lattice points, then you get a particular pattern. Like in this case, you can see a cubical structure. So when such cubes are replicated again and again in the various directions, okay, to the right, to the left, above, below, front, back, and so on, you get the formation of an entire crystal. Okay? So that means it brings us to the definition of the unit cell. So what is the unit cell? It is nothing but the smallest repeating structural unit of any crystalline solid. Now remember, these lines that you can see connecting the lattice points are imaginary lines. In reality, the solids, the constituent particles are compactly arranged. They are very close to each other and there exists no such line. But if we were to imagine such lines, then it would be similar to a pattern of rangoli which goes on replicating in various directions. So this unique pattern or the smallest repeating structural unit of any crystalline solid is what we term as the unit cell. Now, there can be various types of unit cells. Now, to determine the types of unit cells, we need to understand that there are two parameters that define a unit cell. One is the edges and the other one is the angles between the edges. So, if I were to imagine that unit cell on the X, Y, and Z axis, then I can assume that the edges lie on the three axes, that is the X axis, the Y axis, and the Z axis. So if one of the edge length is named as A, the other one as B, and the third one as C, then the angles between the edges A and B is denoted as gamma, while that between the edges B and C is denoted as alpha, and the angle between the edges C and A is denoted as beta. Once we know the measure or the relation between the edges and the angles of any unit cell, then we can determine 7 different types of unit cells. So let us see these 7 different types of unit cells. So the first one here is the very simplest one, that is the cubic unit cell, wherein all the edges, that is A, B, and C, are equal to each other, as well as the angles between the edges are all equal to 90 degrees. So this is a cubic unit cell. The second type of unit cell which we have is called as the tetragonal, where two edges are equal to each other. A is equal to B, but the height C is not equal. Okay, so the bases are equal, that is A and B are equal to each other, but the height C is not equal. So in that case, you get a rectangular cuboid, you can say, or it is called as tetragonal, although the angles here are all 90 degrees. The third type is where you have all the edges of different lengths, that is A is not equal to B, is not equal to C. So all three have got different lengths. However, the angles between the edges are still equal to 90 degrees. They are all equal to each other. So such a type of unit cell is called as the orthorhombic unit cell. Then next, we have what is known as the monoclinic unit cell, where again the edges are not equal to each other. That is, A is not equal to B, is not equal to C. However, the angles out of the three angles, alpha and gamma are equal to 90 degrees, but it is not equal to beta. That is, the beta angle is not equal to 90. Then such a unit cell is said to be of the monoclinic type. Next, we have the hexagonal type, where two edges are equal, that is A is equal to B, but it is not equal to the height, that is it is not equal to C, something like the tetragonal. But here the angles alpha and beta are equal to 90. However, the internal angle gamma is not equal to 90, rather it is equal to 120 degrees. Then this gives rise to a hexagonal structure. So we call it as the hexagonal unit cell. The next type is the rhombohedral, where all the edges are equal to each other and all angles are also equal to each other. However, the angles are not equal to 90 degrees. So a rhombohedral is, you can compare it with the cubic. So like a cubic, in rhombohedral also all the edges are equal to each other and all angles too are equal to each other. But what differentiates a rhombohedral from a cubic is that the angles do not measure 90 degrees. And then we have the last type of unit cell, the seventh type, which is the triclinic, wherein all the edges are not equal to each other, all the angles are also not equal to each other, and they are not equal to 90 as well. Okay, so none of the angles are equal to 90 degrees and the edges are also not equal to each other. Then it gives rise to a triclinic. In monoclinic, you saw that two of the angles, alpha and gamma, are equal to 90 and only beta is not equal to 90. Here in triclinic, all the three angles are not equal to 90 degrees and all the edges are also not equal to each other. So this gives us the 7 types of unit cells. Now these 7 types can further be expanded to 14 types of unit cells, or what we call as the Bravais lattices. Okay, now what do you mean by these Bravais lattices? You saw just now that the lattice points, or the points at which the constituent particles are present, were only at the corners. Okay, but instead of having the constituent particles only at the corners, if the particles happen to be elsewhere also in the unit cell, then it gives rise to some various types. So let us consider first the cubic type. Now in the cubic type, as you can see here, these red dots denote the position of the constituent particles in the unit cell. So if these constituent particles are present only at the corners of the unit cell, it is called as a simple or a primitive cubic unit cell. Whereas if you have the particles at the corners as well as you have them on the faces of the cube. Okay, remember the cube has got 6 faces. So if there is one particle on every face. Okay, so there is, you can see here the representation of 6 blue dots. So each blue particle is on the face of the cube. Okay, on the top, at the bottom, then on the right side, on the left side, on the front face as well as at the back face. So in all 6 dots you can see here. So if the particles are present in addition to the corners, also on the faces, then it is said to be a face-centered cubic unit cell. And if you have the constituent particle present at the corners and along with that you have a single particle present exactly in the center of that cube, then it is said to be a body-centered cubic unit cell. So this gives rise to 3 types of cubic unit cells. One is the simple or the primitive cubic unit cell, where the particles are present only at the corners. The face-centered cubic unit cell, where the particles are present on the faces of the cube in addition to all the 8 corners. And the third type, where the particle is present in the center of the cubic unit cell in addition to being present at all the 8 corners. So this is called as the body-centered cubic unit cell. So these makes it 3 more types. Then you also have in the tetragonal, you can have 2 more types. That is, you can have the simple tetragonal. Like the simple cubic, here also the constituent particles are present only at the corners of the tetragonal unit cell. And the body-centered tetragonal unit cell, where like the body-centered cubic, there is one constituent particle in the center or exactly in the middle of the body of the tetragonal unit cell, in addition to the particles being present at the corners. So this is the body centered tetragonal unit cell. In the hexagonal type, we do not have any further types. We just have the simple hexagonal. It is also called as the hexagonal only. So the constituent particles are present only at the lattice points or only at the corners. Now coming to the monoclinic. Monoclinic, again, you can have two types. You can have the simple monoclinic with the particles only at the corners, or you can have what is known as the base-centered monoclinic. Now, what do you mean by the base-centered? Base-centered means where the particles are present only at the base faces. That is on the bottom face and the top face. So only at the top and the bottom face, the center of the top and the bottom face, if the particles are present, then it is called as base-centered. In the face-centered, as you saw in the cubic, face-centered cubic, there is a particle at the center of every face of the cube. So there are 6 particles here, the 6 blue colored particles. Whereas in the base-centered, there are only 2 particles on the top face and at the bottom face. That is called as a base-centered. So in monoclinic, you have 2 types, the simple monoclinic and the base-centered monoclinic. Next, we have the triclinic. Again, in this triclinic, there is only a single type, that is the simple one or the primitive one. So it is simply called as a triclinic unit cell. Now, after this, we have the rhombohedral. Again, there is only one type of the rhombohedral unit cell also. Now, coming to the orthorhombic. In orthorhombic, you can have 4 different types of unit cells. The first one is a simple rhombohedral. Simple orthorhombic, simple orthorhombic, where only at the corners the particles are present. The next, you have the body centered, where there is a single particle in the center along with the corners. Then you have the base centered, that is on the top face and the center bottom face. At the center of both the faces, you have an extra particle. And then you have the face centered, where there is a particle at the center of every face of this orthorhombic unit cell. So in all, if you see, there are 14 different types of lattices, and these are called as Bravais lattices. So there are 14 different types of Bravais lattices. So every crystalline solid, when you ultimately break down to its smallest particle possible, you will see that it is comprised of a unit cell, and the unit cell can be one of these 14 types. Now in this chapter, we'll be studying the unit cell in more detail to see how exactly the particles are arranged or how they are packed into the solid to give the ultimate crystalline structure. Now, your syllabus has dealt with only the cubic type. So we will be concentrating only on these top 3 Bravais lattices, that is the simple cubic, the face centered and the body centered cubic unit cells. So let us now understand how the constituent particles are exactly arranged. Okay, so for that we are dealing with these 3 cubic unit cells, which is there for your syllabus. That is the simple cubic, the face centered and the body centered. Now what you can see here is called as the ball and stick model. So if I have to imagine the constituent particle as a ball, the imaginary line as a stick, so this is called as a ball and stick model. Now this does not give us a complete idea about the packing of the solid, and so we refer to this particular kind of a arrangement, which is a 3-dimensional arrangement. So here you can see how the particles are compactly arranged, they are touching each other. There is no intermolecular space, or intermolecular space is the minimum over here. Now this is a cross-sectional view of this 3-dimensional structure. So as you can see here, when you take the cross-sectional view at the corners, you don't have the complete atom. You don't see the complete sphere as you can see here. It is only a part of the sphere. Okay. Later on, we'll be dealing in detail, and you will understand that at every corner, there is only 1/8 of a sphere or 1/8 of the atom at every corner of the unit cell. So this is the simple cubic unit cell. Now this one is the face centered, where you can see the red colored dots represent the atoms at the center of every face, whereas the yellow colored ones indicate the atoms at the corners of the unit cell. So this is how the 3-dimensional picture will look, and the cross-sectional view gives you a better idea. So here you can see on the faces, the red colored atom is only half. The entire atom is not present at the center, but it is actually only half of it. And again at the corners, you have only 1/8 of an atom. Now coming to the body center, there is a single atom in the center of the cubic unit cell along with the corners, the 8 corners. So this is how the three-dimensional view looks. But when you take the cross-sectional view, you understand that again at the corners, there is only 1/8 of the atom, whereas in the center, that atom is completely belonging to that unit cell alone. So this is the body-centered cubic unit cell. So now with the knowledge of these unit cells, let us see how to replicate this in various directions and get the complete pattern or the complete structure of the crystalline solids. That is, let us understand about packing in solids. So in today's session, I'll be just covering the one-dimensional and two-dimensional arrangements, and we'll delve into the three-dimensional arrangements in my next lecture. So suppose I were to arrange these atoms in one dimension, then this is how I would be able to arrange them. They're just placed one after the other, all in a single row. Now, as I place these atoms all in a single row, one after the other, if I were to pick out on one particular atom, let us say this one which is highlighted in pink, then you can notice that this atom in pink is in contact with two other atoms, one on the right and one to the left of it. That means this pink colored atom is in contact with two other atoms in this particular one-dimensional arrangement of the atoms. This is very much similar to a string of beads. So each bead in that string will be in contact with two other beads. And the number of atoms or number of particles with which a particular particle is in contact with during an arrangement is called as its coordination number. So in this case, the coordination number will be 2 because each atom here is in contact with or it is touching two other spheres, one to its right and one to its left. I hope this is clear. So coordination number is nothing but the number of atoms or number of constituent particles with which a given particle is in contact with. Now, let us understand, suppose the same one-dimensional arrangement I'm converting into a two-dimensional packing. So this two-dimensional packing, I take one string of beads or one row of beads and I go on arranging rows after rows, one above the other. So as you can see here, the first row is exactly identical to the second, which is identical to the third and the fourth and so on. The atoms are all placed in alignment with each other. Every row, the atom or the beads are exactly one above the other. So this is said to be a proper alignment wherein the particles are lying exactly one above the other. So because of this kind of an arrangement, the rows are all identical to each other. So I can say if I call the first row as row A, then the second row is also identical. So I can call it also as row A. The third row also can be termed as row A and so on. That means this type of a two-dimensional packing can be referred to as the AAA type of two-dimensional packing. Now in this type of packing, what is the coordination number? So again, if I pick out any one atom over here, let us consider this particular atom for example. Now coordination number means the number of atoms with which the particle under consideration is in contact with. So you can see here this particular atom is touching four other atoms, one to the right, one to the left, that means in the same row like the one-dimensional packing. And then because you have stacked some rows below it and above it, okay, so you will have one below and one above. That means in all, this particular sphere is in contact with four other spheres and hence its coordination number will be 4. All right. So this is an example of AAA type of two-dimensional close packing. This is called as two-dimensional because you can see here there is only 2 dimensions. Let us say this is the length of the arrangement. Then this will be the width or the breadth of the arrangement. So you can place strings of beads one over the other, okay, one beside the other rather, on a table. So then you can see it is a two-dimensional flat arrangement where the coordination number will be 2 because each sphere will be in contact with 4 other spheres, 2 in the same row and 1 above or in the next row and 1 below or in the behind row. So the coordination number becomes 4. Now there is one more type of two-dimensional packing that is possible. That is if I were to arrange the rows in such a manner that The first row of beads I've already placed. Now when I get the second row, I place it in such a manner that the particles or the beads fit into the depressions of the first row. So you can see here this sphere or this atom is fitting into the depressions formed by the particles in row A. Okay, so this gives me a different kind of an alignment for this particular row. So if I were to name the first row as row A, the second row would be termed as row B. Now again the third row is identical to the first. The third row again fits into the depressions of the second row. Okay, all these atoms are fitting into the depressions formed by the second row. This is something similar to the arrangement of the chairs in an auditorium. For better viewing, when you go to a theater, you must have seen the chairs are arranged in such a manner that the first row and the second row chairs will be exactly between the chairs of the first row. Okay, so similarly here, the atoms or spheres of the second row are fitting into the depressions of the first row. This makes the alignment of the second row different from the first. So if I were to name the first row as row A, the second row would be termed as row B. Then again the third row becomes identical to the first. So I can once again call it as row A. The fourth row becomes identical to the second. So I can call this as row B and so on. So this type of a packing would be called as AB type of two-dimensional closed packing. Okay, now again this is two-dimensional because this has got only the length and let us say this is the width or the breadth. Okay, so if I were to place the string of beads on the table such that the second row fits into the depressions of the first and so on, I go on adding more and more rows, then I will get a set of rows on the table, and that is why it is a two-dimensional kind of packing. Now what is the coordination number in this case? So if I were to consider any one central atom over here, I can see that this particular atom is in contact with two other atoms in the same row. At the same time, it is in contact with two other atoms from the next row, adjacent rows, one to the right of it or above it, I can say, and below it. That means in all, this particular sphere is in contact with six other spheres. Okay, so because it is in contact with six other spheres, we are getting a hexagonal shape here. So this indicates the coordination number or the number of atoms with which this particular atom in this packing is in contact with is equal to 6. Therefore, the coordination number in the two-dimensional AB type of packing is 6. So today we've understood what is one-dimensional and two-dimensional packing. Now we need to understand the three-dimensional arrangement of the particles in a crystalline solid. So this we will take it up in the upcoming lecture. Until then, do keep watching and do suggest my video to your friends and ask them to subscribe too so that they are able to understand and get clarity on this particular topic. So see you in my next lecture. Bye. And don't forget to leave your comments. Thank you.